You can start now.
Thank you, Mateus. Welcome everyone to today's seminar. It's a pleasure to introduce Sara Saracino from the Liverpool John Moores University in the United Kingdom, where she's a postdoctoral research assistant since 2019. Before Liverpool, Sara held a postdoc position at the University of Bologna in Italy. Sara obtained her master's and PhD degrees in 2014 and 2017, respectively, at the University of Bologna, with a period abroad in Chile, in Concepcion, working with multi-conjugate adaptive optics to study bulge globular clusters. Thank you so much, Sara, for accepting our invitation. You may start when you're ready.
Yeah, thank you, Anna. So first of all, I would like to thank you all for inviting me to talk to you here today. So what I want to talk to you about is work that I have been doing in the past 2 years with lots of colleagues at LJMU in Liverpool. So in particular, I want to talk to you about the phenomenon of multiple population in globular cluster and how it manifests itself through the cosmic time. So first of all, I want to, sorry, I can, why I can, I don't know why.
Maybe stop sharing and share again. Ah, worked.
Oh yeah, I don't know how I make it working really. Oh, remote control.
It's working now, yes.
Yeah, but it's working. Ah, okay. But how I can? Okay, sorry. So let's start from the very basis. Since like I really know that all of you know about globular cluster, but just to put everyone on the same page, let's talk about globular cluster and like what they are. So these are actually the oldest and the densest stellar aggregates in the universe. They contain, on average, 10 to the 5 stars with chemical masses from 10 to the 4 to 10 to the 6 solar masses. So actually, globular clusters have been used during the last years and decades as tools for many different things. For example, to determine the structure of the Milky Way, since they have been thought to be a prototype of simple stellar population, they have been used to understand and calibrate the stellar evolution models, as well as to constrain the formation and evolution of the Milky Way and external galaxies, since we know that globular cluster systems are actually different for different galaxies. Also, since they are very dense and very compact, these kind of objects are really are really the place where very exotic events can happen, and also objects like millisecond pulsars or low mass X-ray binaries can really happen to be. So this is the general picture about globular cluster and what is the traditional view of globular clusters. So as I said before, so they were considered as the prototype of simple stellar population, so that all the stars in a globular cluster should share the same age and the same chemical abundances. So, for example, if we go back to the early 2000, for example, from observation using the Hubble Space Telescope. So you usually looked at these very nice CMDs with single sequences in the optical filters, for example. And so the idea was, yes, they are simple stellar population. But once people have started to look more and more into the details of all these CMDs, they have started to see multiple sequences or spreads in their evolutionary sequences. For example, this is an example of the main sequence of NGC 2808, which is a galactic globular cluster. And actually you see that in optical colors as well, once you have the very good accuracy, photometric accuracy, you start to see multiple sequences there. So then we were quite sure that globular cluster couldn't be considered anymore as simple stellar population, because actually all the different sequences, so if you look at the SGB, at the RGB or the main sequence, all of these sequences are not as a single one, but they all show some peculiarities. So this is an indication that there is something there that we actually called as multiple stellar population. So what does it mean? Multiple population actually manifest themselves as star-to-star light element abundance variation, like of the stars within the same cluster. And actually, just to give you an example, this is the manifestation of multiple population in specific colors. Like photometrically has these multiple sequences or a larger spread, where actually these are the normal stars and these are the anomalous, so-called anomalous star with these light element abundant variations. And this is actually how this translates spectroscopically into this typical anti-correlation or correlation between different elements. So this is something that people have looked for many, many years now in a great detail. And actually all globular clusters show anomalies, but all of them, they are all unique in the sense that all of them differ into the details. So actually, when you look at photometrically at globular cluster and you look in the optical or in the ultraviolet, then you see that these multiple sequences are always there, but they trace different abundance variations. For example, if you look at optical colors here on the right, you see that these multiple sequences are actually due to structural changes, in the sense that this is not an effect due to stellar evolution. This is due to an helium enhancement from the first to the last sequence here. And since all these stars are in the main sequence, they should have actually born with this helium enhancement. While if you look at ultraviolet colors, then you see the same situation, but all these different sequences are tracing different elements, in the sense that here you see that spread in nitrogen and carbon, especially, are actually manifesting here. So probably a very simple question that is really fundamental here could be that, oh, maybe age is driven the presence of these sequences here. So I can tell you now, but I'll show you later why age is not really driving the differences that you see here. Because, for example, a literature work in about the galactic globular cluster tell you that if there is a difference in age between the population within a single cluster, then it should be like less than 300 mega year. And actually, this is an upper limit. With ancient globular cluster, we cannot do much more than this. So much better than this. So, okay, we now know that globular clusters are not simple stellar population. Then we need to consider another traditional let's say opinion about globular clusters, so that okay, they are all predominantly old, like with an age of more than 10 gigayear. They are all like most of them are metal poor. Okay, so probably they could only form in the special conditions of the early universe, and for this reason multiple populations are manifesting there for some specific condition that are not present in the local universe. Okay, so to test this hypothesis, one easy let's say thing that one can do is to compare, for example, globular clusters with young massive clusters. So just to give you an idea, this is a picture of omega Sen that is not really like the prototype of a classical GC, as we all know, since it's the remnant of a galaxy that has merged long ago with the Milky Way. But anyway, the idea here is to show you how a globular cluster look like. This is a few million solar masses and with an age of more than 12 gigayear or so. So actually, if you go, for example, in the antenna galaxies, this is an image from HST, and you zoom in into this region, then you start to see some objects like this one. So these are very, very dense and very compact, and but they are only 7 mega year old. So actually what you see here is that in terms of masses, in terms of sizes, they, like both globular cluster and young massive cluster, share the similar properties, so that we can actually say that these are the same manifestation of these kind of objects. So we can say that globular clusters are still actually forming in the local universe. And so this is something that maybe omega Sen or other cluster like this one would look like very early in the like in the very early stage of its formation and evolution. So, okay, just to recap and go back to the multiple population side, we have a list of observables from all the observational studies that have been done so far. So we actually see all these anti-correlation between different elements like sodium, oxygen, or nitrogen, carbon, which are the more the more popular ones, let's say. But also we see that there are some other elements varying, like magnesium or aluminium, but for example no spread in iron or in calcium, and this can already tell us something about what can be the like the stars that really make this abundant variation happen within the cluster. So for sure we can remove the idea that multiple population can be somehow related to like metallicity dependent somehow, because globular cluster with multiple population have been observed in metal poor regime and metal rich ones. So, so that actually we have to find somewhere else the origin of this multiple population. And so people, theoreticians, have tried many times to think of a way to explain the origin of multiple population, but I should say that none of the scenarios that have been put forward so far really match with all the observational constraints that have been discovered so far. But for sure, we know that all these ingredients, like all these elements that we know that vary in these globular clusters, actually are caused by like are responsible of the hot bottom burning phase, which happen for very massive stars. And so this is the reason why all the scenarios actually try to consider as polluters very like high massive stars as AGB stars that are quite massive stars, very quite evolved stars, or other kind of objects like interactive massive binaries or extremely massive stars. But yeah, this is kind of naive, but just to give you a brief cartoon on how do this process of multiple population work, I will show you like how the AGB scenario is developed, but like all these kind of scenario are based on the same assumption, so that we can consider like this valid for all of them. Okay, so you have this first generation of stars that form with all these red dots here. Then after about 30 mega year or so, all these massive stars evolved into the AGB sequence, and so that they starts to shed material around, and all this material collect in the center of the cluster, so that at some point the cluster really need to accrete some additional gas to create the second generation of star. And so this is like an ad hoc assumption, so that we can get at the end like all what the observational tell us about. So that okay, you have this pristine gas that is accreted by these clusters, so that you can actually form a second generation of stars that is sicked into the cluster center. But okay, after this, again, you don't have the abundant ratio that are observed in the right numbers, so that you really need to lose most of the mass that is embedded in the first generation, so that like almost 95% of the first generation of stars need to be lost, so that you get the abundant ratio right between the first and the second generation. So that you see actually that there are some prediction of this formation scenario, but this is a really ad hoc scenario, so that can maybe respect some observational constraint, but it fails in like representing all the others. So for example, to give you an idea, one of the prediction of this formation scenario is that the second generation is more centrally concentrated, and this is actually true, like at least for most of the globular cluster that we observe. We see that the second generation is more centrally concentrated than the first one. So in this case, actually, the prediction is confirmed. But then you have other predictions that are actually contradicted by observation, as the one that you need to have enough material to form the second generation of stars, so that globular cluster must have been 10 or 100 times more massive than presently seen. And this is the so-called mass budget problem that you can actually disprove, saying that if you go and look, for example, at dwarf galaxies and you count in the same metallicity bin how many stars you have in globular cluster compared to the field, and then you see that these 10 to 100 times more stars are not observed there. So you have a ratio of 4, but no more than this. Then you have that clusters can retain stellar ejecta and accrete gas for a long period, but this is a prediction that we can't really test. But we can test the last one, the last prediction, so that massive cluster. So if we assume that these this scenario are based on multiple bursts of star formation, then if you go to very young massive clusters, like more than 10 megayear or so, in the range then like where you would expect to see ongoing star formation, you should see this. But again, this has been done in the literature, and there was no evidence for ongoing star formation in these young massive cluster. Okay, so this is the picture, but then you can think, okay, but if you really consider that young massive cluster are the same object as globular cluster, but are only just much younger, why you don't go to this young massive cluster to look for the presence of multiple population? Yes, so this is actually what our group in Liverpool has been done for quite a while now, with this HST survey of massive clusters in the LMC and SMC, because we are quite lucky that we have these two galaxies that have clusters from very young to very old, so that we can actually test the possibility to find multiple population in clusters that are younger than 10 gigayear, as for the Milky Way ones. And so the power of this approach was to use a dedicated filter with HST, which is a narrow filter that really is able to pick up variation in nitrogen and oxygen. And so this was really the power of all this kind of study. And so just to give you an idea, this was the situation before we started our survey of LMC and SMC clusters. So we had that all the old Milky Way globular clusters showed presence of multiple population, and this was very well established and well known. Then we added all these dots here that were the first target that have been observed with HST in this survey. And so I have highlighted here NGC 121, which is the oldest cluster in the SMC, for only one reason, because we went to this cluster, which is old, and we were expecting to find multiple population there. So if not, this was would have been a big surprise, and like no one have ever really trust all the other results. Okay, so we did this. We checked for for the presence of multiple population in NGC 1-to-1, and we actually find the evidence is there. So we were happy, and we went to this other group of stars, so of cluster, intermediate age cluster from 6 to 8 gigayear from both galaxies. And actually, I want to show you just a case of LISTE 1, which is one of these bunch of clusters, which is a 7.5 globular cluster in the gigayear-old cluster in the SMC, which is quite massive, more than 10 to the 5 solar masses. And actually, you see both from the photometrical point of view and from the spectroscopical point of view, you see that there is a clear evidence for nitrogen spread. So here you are looking at the RGB stars in this specific filter combination that is able to to manifest these differences in nitrogen. And actually, for some stars here in the two Gaussians here, we went to observe them spectroscopically, and actually what you see here, there is a clear spread in nitrogen also from the spectroscopical point of view. Okay, so multiple population here as well. So we were very excited about these results, so that like in all these other clusters, we find the same result, and we were quite sure that we were going to find multiple population everywhere. But this was not the case, and I can tell you this story because we next wanted to look at NGC 419, and we were very, very surprised that this is a 1.5 gigayear-old cluster, still quite massive. And but we realized that actually we couldn't find any evidence for the presence of multiple population here. So we were quite disappointing. We were quite surprised, but this was the result. So we accepted it, and we decided to go and look more into the detail all these other clusters here, and with quite a surprise, we went to NGC 1978, which is a 2 gigayear-old cluster. And we realized that this was the youngest cluster for which we could find evidence for multiple population, in the sense that probably there is and then we added more and more clusters, and as you can see here, all these clusters show evidence for multiple population. None of them, and also I can add more points here, none of all the others show multiple populations. So then we started to think, like to look at this picture and trying to understand why. And like we don't have yet an explanation for this, but we know, like observationally, that multiple population seems to be present in all the globular clusters and all the star clusters in general, older than 2 gigayear, and with a quite dependence on mass as well. So from a certain mass and from a certain age, star clusters show presence of multiple populations. So the origin of multiple population is not cosmological, and this is the first takeaway message that I want to leave you with. So, okay, now I want to show you some of the very recent constraints that we have started to put on the multiple population phenomenon, with the idea to try and constrain the scenarios that we can actually consider about the origin of multiple population. And for example, I can show you how we can really compare these all these observation coming from extragalactic globular cluster with the one from Milky Way globular cluster. So actually, people in the literature have used this kind of naive filter combination that really help to maximize the information embedded in the multiple population, creating what is called chromosome map. So this is the chromosome map of a galactic GC, though you don't need to really understand all the details on this, but you can just remember that on the x-axis, this is a proxy of the helium abundance here, while in the y-axis, you see a proxy of the nitrogen spread. So these are the two important things to remember. And so the point is to compare like to like a chromosome map created for a Milky Way globular cluster with the one from an extragalactic globular cluster. And this is what we did in 2019, trying to compare the two and see whether they share the same properties or not. And as you can see here, like they really have the same shape, they have the same extension, and of course they differ into the detail, but this is not really unexpected, as I said at the beginning. So actually we can conclude from this test that multiple populations are actually the same regardless of age and environment, at least at the first level, let's say at 0 level. So one other evidence that we got from this survey is that actually if you plot a proxy for the nitrogen spread for all these SMC-LMC cluster versus age, you see that there is a trend actually of of this nitrogen spread to be higher for older clusters compared to younger ones. And this is something that we need to keep in mind. Of course, the correlation is not very tight in the sense that we have only few targets here, but it's quite expensive, like getting new observations from HSD to add more and more points here, but this is what we are trying to do right now. So, okay, this is a second evidence that I want you to remember, so that older clusters seems to show larger abundance spreads compared to younger ones. So, an additional constraint that I want to talk to you about is what concerns the age difference and the possibility that this population that we see within a cluster actually show some age differences. So as I told you at the beginning, with Milky Way globular cluster, you cannot really put stringent constraint on these age differences. They can be like coeval within 300 mega-year, but you cannot say much more than this. So in this case, all the scenarios that invoke multiple bursts of star formation can really be accepted, because you need like more than 30 mega-year as age difference, and should be fine. But now that we have this cluster, for example, NGC 1978, which is the youngest cluster showing multiple population, we can really try to put tighter constraint on this age difference within a cluster. And this is what we have done, for example, in this case and in another case. So the idea here is to go and look at the SGB of this cluster that since it's very young, is very sensitive to age variations, then plotting all these stars here in this super color that help us splitting the population in different, with different nitrogen abundances, like this one, and then select these two different groups of stars. So this dividing these two populations and plot them again into this optical color magnitude diagram. So if you have an age difference here, you should see that there is a split between, for example, red and blue colors, even in this plot here. But what you can actually see when you do this kind of exercise is that actually the age difference that you can see here is essentially 1 more or less 20 megayear, which means that these populations here are coeval within the cluster. So this is the result for one cluster, 1978, but we have recently done the same exercise for another cluster, NGC 2121, and the result is the same. So 6 plus or minus 12 megayears. So again, no age difference here. And actually, the fact that we are dealing with a very young cluster allow us to put very tight constraint on this. And since these are actually coeval, you can say that multiple populations are not linked to multiple bursts of star formation, because actually all these scenarios that account for like a 30 megayear or more as like age difference, time difference between the two population is actually disproved by these kind of observations. And this is actually a crucial constraint for all the multiple population formation scenarios. So now I want to talk to you about something that I have been working very recently, and I'm very I'm very excited about, which is the possibility to actually complement our HST observations, and so all the information that are embedded in the chromosome maps with VLT Muse observations. So VLT Muse spectrograph is an IFU spectrograph that is low resolution, but it's has the power that can really help you to get a lot of spectrum for many stars in in the same at the same time, let's say, so that you have a big sample of stars. So what is the idea behind trying to combine the information with HST and Muse? Is that with the HST, what you can actually do is to create a chromosome map like this one. This is just for to make it very easy and understandable. This is NGC 2808, again, one Milky Way globular cluster with a very huge spread in nitrogen. And so you create a chromosome like this one, then you separate all the population that we see photometrically, and with Muse VLT, so you should consider that all these points that you see here, they actually have been observed with Muse as well. So we have for all of these stars a spectrum, so that all these stars that are belong to a single population, all the spectra are stacked together to get a very high signal to noise spectrum. So one for this one for this one, and like for all of them. So that at the end, if you compare one-to-one all these spectra, you should look for differences in their in their spectra, and then this is a way to get mean abundances for different elements. So this is what Latour and collaborators did in 2019, and actually you see these very nice trends. It's all the correlation and that anti-correlation that we were looking at before for sodium, aluminum, oxygen, or magnesium, that are really very nicely picked up from like using this technique. But of course, this could be a quite easy task because we are looking at 2808, which is very, which has a huge spread in nitrogen and in all the other elements, as you can see here. But what happens if you look at LMC SMC cluster that, as I told you before, have a much smaller spreads in these elements? So this is what we have done for a sample of 3 clusters in SMC, LMC. And for example, this is the example of NGC416, a 6.5 giga-year-old cluster. So for which we created the chromosome map, starting again from these 2 different filter combinations. We split the population using these nice double Gaussians, and we stacked again all the spectra belonging to this population in one single spectrum, and all the other one in another spectrum here. And so these are the results for NGC416. But also, as a comparison, I show you the results for NGC 1978. As you can see, in both the cases, we were able to find sodium spreads also in this cluster. And especially, I want to like to point your attention on these very small sodium spreads that we found for 1978, which is quite quite exciting that we can actually measure this kind of mean spread in sodium with this high level of accuracy. And this is possible for this kind of technique that really stack so many spectra together to get a very high signal to noise spectrum. Okay, so just to conclude, young and intermediate age clusters are really just young globular cluster because they show exactly the same properties, both photometrically and spectroscopically. So here I just want to conclude summarizing very few things. So first of all, that globular cluster host multiple population, and they manifest themselves through chemical anomalies and multiple sequences in their super CMDs. Again, thanks to the HST survey of LMC SMC clusters, we have found that all the clusters older than 2 giga-year show multiple population with a strong influence of age and mass, that there is no age difference in within the stellar population of NGC 1978 and NGC 2121, putting some very tight constraint on the origin of multiple population. But also in the very last part of the talk, I have showed you that the multiple population is the same for both old and young intermediate age cluster because they show spread in nitrogen that are detected via photometry, as well as spread in sodium detected via spectroscopy. But as you have already heard, the origin of multiple population is still a mystery. So we don't know really how these multiple population phenomenon appear and occur in all these stellar objects. So what is the idea for the future is to explore the parameter space as much as possible to add more and more points on this correlation with age for the presence of multiple population, and again to exploit this synergy between HST and MUSE also to really understand if this age limit that we see at 2 gig a year is really real, let's say, really exists, or is only like due to observational limitation. And so probably with Muse, we can really go to much younger cluster and see whether we can pick up this sodium variation there as well. So I think I'll stop here, and I thank you all for your attention.
Thank you very much for your talk, Sara. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them in the channel, and our speaker will try to answer them later. We'll be back next week with a seminar on metals in white dwarf atmospheres as tracers of ancient planetary crusts by Mark Hollins from Warwick University. Stay tuned and follow AstroUrgis in our social media for the semester's events. Goodbye. Now we go to the breakout rooms.